47 years ago, we launched two machines into the void with a simple mission: study Jupiter and Saturn, then drift into the dark. We expected them to last 5 years, maybe 10, if we were lucky. We built them with 1970s technology. 8-track cassettes were cutting edge when Voyager's computers were designed. We gave them less computing power than a modern car key. We pointed them outward and said goodbye. But they didn't stop. They kept transmitting. They kept measuring. They kept going. And now, in the next 10 years, they're about to cross thresholds we never planned for. They're entering regions of space where our models break down, where the physics textbooks run out of answers, where every new data packet rewrites what we thought we knew about the boundary between us and everything else. This isn't about what Voyager discovered in the past. This is about what it's detecting right now, in real time, as it falls deeper into a region of space no human-made object has ever explored. This is about the countdown to discoveries we can barely predict, and the ticking clock that determines how much longer we have to receive them before the silence becomes permanent. The timeline starts now. The signal is already weakening. And what Voyager is about to tell us in its final decade of operation will answer questions we've been asking since before humans could write, and reveal problems we never knew existed. Let's start with where Voyager is right now, not where it was, where it is, at this exact moment, as you hear these words. Voyager 1 is currently over 15 billion miles from Earth. That number climbs by about 1 million miles every single day. It's moving at roughly 38,000 miles per hour relative to the Sun, faster than any object humanity has ever built. It crossed the heliopause, the boundary of our Sun's influence, on August 25th, 2012. That was 12 years ago. Since then, it's been traveling through interstellar space, true interstellar space, the medium between stars. Voyager 2 followed on November 5th, 2018. It's currently about 12.5 billion miles out, moving at 34,000 miles per hour. It crossed at a different location at a different angle during a different phase of the solar cycle. That means it sampled a different slice of the heliopause, different conditions, different magnetic field orientations, different data. That difference matters, because we don't just have one spacecraft in interstellar space anymore, we have two independent sensors, two perspectives, two streams of data telling us what happens when the Sun's reach finally ends and the galaxy's influence begins. And what they're detecting right now in 2024 as they push deeper is not what we expected. The models predicted a clean transition, a clear boundary. You're in the heliosphere, then you cross the heliopause, then you're in interstellar space. Done, simple. 3 regions, 1 crossing, easy to explain. But Voyager is finding layers, structures, transitions within transitions. The heliopause isn't a line. It's a turbulent, shifting, breathing boundary that pulses with the solar cycle. It moves inward and outward by billions of miles depending on the Sun's activity. Voyager 1 and 2 didn't just cross it once. They crossed it, then detected backward-flowing particles that suggested they'd crossed back, then forward again, then ambiguity, then clarity. The data shows that the edge of our solar system isn't a wall. It's more like a shoreline during a storm. Sometimes you're in the water, sometimes you're on the sand, sometimes the tide comes in and you're underwater even though you swear you were on dry land a moment ago. That discovery, that the heliopause is dynamic and layered, rewrites every model of how our solar system interacts with the galaxy. It means the bubble protecting us from interstellar radiation isn't a stable shield. It's a fluctuating membrane. And Voyager is now deep enough on the other side to measure what happens when that membrane fails, what gets through, how much, how often. Right now, Voyager's instruments are detecting cosmic rays at levels 10% higher than when it first crossed. That's a small increase, but it's persistent, and it's accelerating. The deeper Voyager goes, the more radiation it detects, which makes sense. It's leaving the sun's protective influence behind. But the rate of increase doesn't match the models. The gradient is steeper than predicted, which suggests that either our models of galactic cosmic ray density are wrong, or something between here and deep interstellar space is focusing radiation in ways we don't understand. The consequences of that uncertainty are enormous, because cosmic rays aren't just a scientific curiosity, they're a survival problem. High-energy particles from supernova remnants, from distant gamma-ray bursts, from the chaotic magnetic fields of the galaxy, they slam into DNA. They degrade electronics. They make long-duration space travel, the kind required to reach Mars, to establish bases on the Moon, to send humans beyond Earth's magnetosphere, exponentially more dangerous. We've been designing radiation shielding based on models of interstellar radiation density. Voyager is now telling us those models might be too optimistic, that the universe outside the heliosphere might be harsher than we thought, that the bubble protecting Earth isn't just smaller than we hoped, it might be weaker. And in the next 10 years, as Voyager continues deeper, it's going to measure exactly how much harsher. It's going to sample radiation levels at distances no probe has ever reached. It's going to tell us whether the galaxy is a place humans can ever safely travel through, or whether we're trapped in this bubble, surrounded by a radiation field we can't survive. That's the first countdown, the ticking clock on Voyager's ability to measure the radiation environment before its power runs out. And the timeline on that is tighter than most people realize. Voyager's power comes from radioisotope thermoelectric generators, RTGs, plutonium-238 pellets that decay and produce heat. That heat is converted into electricity. It's a brilliantly simple system. No solar panels to fail, no moving parts to break, just atomic decay, turning mass into energy, keeping the spacecraft alive. But plutonium-238 has a half-life of 87.7 years, which means every 87.7 years, half of it decays into uranium-234. The heat output drops, the electrical power drops. Voyager launched in 1977 with about 470 watts of power. Today, in 2024, it's down to about 249 watts. By 2030, it'll have roughly 220 watts. By 2036, maybe 190 watts. Every instrument on Voyager requires power. The cosmic ray detector, the magnetometer, the plasma wave instrument, the low-energy charged particle sensor, the transmitter that sends data back to Earth, the heaters that keep those instruments from freezing in the minus 270 degrees Celsius void of interstellar space. NASA has been rationing that power like a miser counting coins. In 2019, they shut down the heaters for the cosmic ray instrument. They expected it to freeze and fail within months. It didn't. It kept working. Still works today, operating 45 degrees Celsius below its design temperature limit. In 2023, they disabled a backup thruster system to save a few more watts. Every year, they make harder choices. Every year, they turn something off to keep the most critical instruments alive a little longer. The current estimate is that Voyager 1 will have enough power to operate at least one scientific instrument until approximately 2036. That's 12 years from now. Voyager 2 might last until 2034, maybe 2035 if they're aggressive with shutdowns. That means the countdown has already started. We have 1 decade, maybe 12 years if we're lucky, to extract every remaining piece of data Voyager can give us about interstellar space. After that, the signal stops. The instruments go dark. Voyager becomes a ghost, a tomb, a monument hurtling through the galaxy with no way to tell us what it sees. But here's the tension. The deeper Voyager goes, the more interesting the data becomes. The most important discoveries are still ahead. The transitions it's about to measure, the ones we'll discuss in the coming sections, are the ones that will define our understanding of the galaxy for the next century. But we're running out of time to receive them. 10 years. That's the window. That's the countdown. That's how long we have to catch the transmissions before the power dies and Voyager goes silent forever. And in those 10 years, Voyager is going to pass through regions of space we've only theorized about. It's going to sample the transition zone between the heliosphere's influence and the pure interstellar medium. It's going to detect, if our models are correct, a bow shock, a pressure wave in the interstellar medium caused by our solar system's motion through the galaxy. Think of it like this. The Sun is moving through space at about 450,000 miles per hour relative to the local interstellar medium. It's not stationary, it's ploughing through a sea of gas and dust and cosmic rays like a boat cutting through water. And just like a boat creates a wake, the Sun creates a disturbance in the medium it's moving through. That disturbance is called the bow shock. It's a region where the interstellar medium compresses and heats up as it collides with the heliosphere. For decades, we assumed it existed. Models predicted it. Scientists drew diagrams of it in textbooks. It was supposed to be out there, somewhere beyond the heliopause, a few billion miles further out. But Voyager 1 didn't detect it. Voyager 1 crossed the heliopause and kept going and didn't find a bow shock. Which means either the models are wrong, or the bow shock is further out than we thought, or it's structured in a way that Voyager's instruments can't detect. Or, and this is the option that keeps astrophysicists awake at night, it doesn't exist at all. If the bow shock doesn't exist, that means our understanding of how stars move through the galaxy is fundamentally incomplete. It means the Sun's interaction with the interstellar medium is governed by physics we don't yet understand. It means every model of stellar motion, of galactic magnetic fields, of how cosmic rays propagate through space, needs to be revised. But if it does exist and Voyager just hasn't reached it yet, then it's still out there, waiting, and Voyager is closing in on it at 1 million miles per day. Current estimates place the bow shock, if it exists, somewhere between 230 and 400 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Voyager 1 is currently around 164 astronomical units out, which means, if the bow shock is real, and if it's on the lower end of the prediction range, Voyager could reach it within the next 5 to 7 years, right in the middle of the power countdown. Imagine that moment. Voyager running on fumes, instruments failing one by one, transmitter barely holding on. And suddenly the plasma wave detector lights up. The magnetic field readings spike. The cosmic ray counts shift. All the signatures we've been predicting for 50 years, all appearing at once. But we'd only have months to study it, maybe a year, Because by the time Voyager reaches the bow shock, if it exists, the spacecraft will be in the final stages of its life. Every watt will matter. Every transmission will be rationed. We'd have one chance to capture the data, one crossing, one fragile aging machine, 15 billion miles from home, sending back the most important readings of its entire mission in its dying breaths. That's the gamble. That's the countdown. That's why the next 10 years matter so much. But the bow shock isn't the only discovery on the timeline. It's not even the most urgent one. Because right now, in real time, Voyager is detecting something unexpected. Something that doesn't fit the models. Something that suggests the interstellar medium isn't uniform, isn't stable, isn't the calm, empty void we thought it was. Voyager's plasma wave instrument has been picking up oscillations, ripples in the density of the interstellar medium. Not random noise, not instrument error, structured patterns, waves propagating through space at speeds that suggest they're being driven by events far outside our solar system. These aren't local disturbances. They're not echoes of solar activity. They're waves in the fabric of interstellar space itself. Density fluctuations in the thin gas that fills the space between stars. And they're coming from directions we can't yet pinpoint. The working hypothesis is that these are shock waves from distant supernovae, stars exploding hundreds or thousands of light years away, sending ripples through the galaxy that take millennia to reach us. Voyager is detecting the aftershocks of stellar deaths that happened before humans existed, before dinosaurs, before complex life on Earth. But here's the problem. The frequency and intensity of these waves don't match our models of supernova distribution in the Milky Way. If we're detecting this many shock waves at Voyager's current location, it suggests either there are more supernovae happening nearby than we thought, or the interstellar medium is more turbulent than predicted, or these waves are being amplified by structures in the galaxy we haven't accounted for. And in the next 10 years, as Voyager moves deeper into interstellar space, it's going to measure how these waves change with distance, whether they get stronger or weaker, whether they're isotropic or directional, whether they're a constant background hum or discrete events with identifiable sources. That data will tell us how energy propagates through the galaxy, how supernovae shape the structure of interstellar space, how the radiation environment between stars changes over time, how often Earth is bombarded by these waves, and whether they've had any effect on our planet's history. Because here's the uncomfortable question lurking beneath all of this. If Voyager is detecting shock waves from supernovae that exploded thousands of years ago, and if those waves are powerful enough to create measurable density changes in the interstellar medium 15 billion miles from Earth, then what happens when a supernova goes off nearby? Not thousands of light years away, nearby. Within 100 light years, within 50, within 10. We know it's happened before. We found isotopes in Earth's geological record, iron-60, plutonium-244, that could only have come from a nearby supernova. The signatures are buried in ancient ocean sediments, in Antarctic ice cores, in the crusts of deep-sea manganese nodules. They tell the story of at least 2 supernovae that exploded close enough to Earth to shower our planet with radioactive debris, one about 2.6 million years ago, another around 8 million years ago. We don't know what effects those events had. We don't know if they triggered extinction events, climate shifts, mutations. We don't know if they were just background noise in Earth's already chaotic radiation environment, or if they were catastrophic. But Voyager is giving us the tools to answer those questions, Because by measuring the structure of shock waves in the interstellar medium, by sampling the radiation density at different distances from the Sun, by detecting the ripples of ancient stellar explosions, Voyager is building a map of how energy moves through the galaxy. And that map will tell us how vulnerable we are, how often these events happen, how much warning we'd have if a nearby star went supernova tomorrow. That's not a hypothetical exercise. Betelgeuse, a red supergiant in Orion, is showing signs of instability. It's dimmed unexpectedly. Its outer layers are behaving erratically. It could explode tomorrow, or in 100,000 years. We genuinely don't know. And when it does, it'll be the brightest supernova visible from Earth in recorded history. Bright enough to cast shadows at night, bright enough to be visible during the day. And the radiation wave will follow, the shock wave, the particle storm. Betelgeuse is about 650 light-years away, far enough that the radiation won't sterilize Earth, but close enough that it will absolutely affect our magnetosphere, our upper atmosphere, our satellites. And we have no precise models for what that impact will look like, because we've never measured a supernova shockwave directly. Voyager is giving us the first data to build those models in real time, right now. And in the next 10 years, as it samples deeper regions of interstellar space, it's going to refine those models. It's going to tell us whether the galaxy is a shooting gallery we've been lucky to avoid, or whether the radiation environment is more forgiving than we feared, but only if we can keep the instruments alive long enough to receive the data. Only if the power holds out. Only if the transmitter keeps transmitting. And that brings us to the second countdown, the one that's even tighter than the power budget. The countdown on our ability to hear Voyager at all. Voyager's signal is fading, not because the transmitter is failing. It's still working exactly as designed. It's fading because of distance, because of physics, because of the inverse square law, which is one of the most merciless rules in the universe. Here's how it works. When Voyager transmits a signal, that signal spreads out in all directions. It's not a laser beam pointed straight at Earth. It's a cone of radio waves expanding into space, and as that cone expands, the energy gets diluted, spread thinner, weaker. The math is simple and brutal. Double the distance and the signal's strength drops to 1/4. Triple the distance and it drops to 1/9. It's not linear. It's exponential decay. And Voyager is now so far away that the signal reaching Earth is almost unimaginably faint. Right now, Voyager 1's transmitter is broadcasting at 23 watts. That's about the same power as a refrigerator light bulb. And by the time that signal crosses 15 billion miles of space, by the time it reaches the deep space network antennas on Earth, it arrives with a power of about 0.1 billion billionths of a watt. That's not a typo. That's 10 to the minus 16 watts, 100 femtowatts. It's a whisper. A ghost. The faintest artificial signal humans have ever tried to detect. To put that in perspective, the total amount of energy collected by all the deep space network antennas from all the Voyager transmissions over the entire 47-year mission, if you added it all up, would be less than the energy required to melt a single snowflake. And yet, we're still hearing it, we're still decoding it, we're still pulling scientific data out of that infinitesimal whisper crossing the void. But it's getting harder. Every year, Voyager moves another 350 million miles further out. Every year, the signal gets weaker. And there's a threshold, a hard physical limit, where the signal becomes so faint that even the most sensitive antennas on Earth can't distinguish it from background noise. We're approaching that threshold. Fast. The Deep Space Network is a collection of three massive antenna complexes, one in California, one in Spain, one in Australia, spaced around the globe so that at least one is always pointed at Voyager. Each complex has a 70-meter dish, that's 230 feet across. Enormous, sensitive, built specifically to communicate with spacecraft at the edge of the solar system. But even those dishes have limits. The noise floor, the level of random electromagnetic interference from the galaxy, from Earth's atmosphere, from human technology, creates a baseline hum that the signal has to rise above. If the signal drops below that noise floor, it's gone, unrecoverable, lost in the static. Current estimates suggest that Voyager 1's signal will drop below the detectable threshold sometime around 2036. That's the same year the power budget runs out, two independent countdowns, both converging on the same deadline. After that, even if Voyager's instruments are still working, even if it's still collecting data, we won't be able to hear it, unless we build a bigger antenna. NASA has been exploring options. There are proposals to construct a 100-meter dish specifically for deep space communication. Proposals to use arrays of smaller dishes working in concert. Proposals to use radio telescopes like the Very Large Array in New Mexico as backup receivers. But none of those projects are funded. None are under construction. They're all contingency plans, ideas on paper. Which means the current timeline stands 12 years, give or take, before Voyager's signal fades into silence. 12 years to capture everything it can tell us about the interstellar medium, about cosmic rays, about the bow shock, about the structure of the galaxy. 12 years before we lose contact forever. But here's the twist that makes this countdown even more urgent. The data rate is already dropping. Voyager doesn't transmit everything it detects in real time. It can't. The bandwidth is too limited, so it stores data on an internal tape recorder, an actual magnetic tape system, the same technology used in cassette decks, and plays it back in slow, compressed bursts. Right now, Voyager's downlink rate is 160 bits per second. That's slower than a 1990s dial-up modem. It takes hours to transmit what a modern smartphone could send in a fraction of a second. And as the signal continues to weaken, NASA has to lower the data rate even further to maintain reliability. By 2030, it might be down to 40 bits per second. By 2035, maybe 10. That means the discoveries Voyager makes in its final years, the most distant measurements, the deepest samples of interstellar space, will come through in agonizing slow drips. A few bytes per minute, critical data fragmented across weeks of transmission time, and if there's a glitch, if the signal drops for even a few hours because of atmospheric interference or antenna maintenance, that data might be lost. This is the nature of the countdown we're living through. It's not a dramatic shutdown. It's not a single moment where Voyager goes dark. It's a slow fade, a gradual decline. Every year the signal a little weaker. Every year the data a little slower. Every year the window a little narrower. And in that narrowing window, Voyager is racing against time to answer questions that become more urgent the deeper it goes. One of those questions is about the local interstellar cloud. Right now, our solar system is moving through a structure called the local interstellar cloud, sometimes called the local fluff, a term astrophysicists use with zero irony, which tells you how seriously they take themselves. It's a region of slightly higher density gas and dust, about 30 light-years across, part of a larger structure called the local bubble. The local bubble is a cavity in the interstellar medium roughly 300 light-years across, carved out by ancient supernovae that exploded millions of years ago. The shock waves from those explosions swept the gas outward, creating a low-density void surrounded by a shell of compressed material. We're inside that void, inside the bubble, and the local interstellar cloud is a wisp of gas floating inside the bubble, probably a fragment left over from the original explosions. We've known about the local interstellar cloud since the 1970s. We've measured its density, about 0.3 atoms per cubic centimetre, which is a near-perfect vacuum by Earth standards, but dense compared to the average interstellar medium. We've measured its temperature, about 6,000 Kelvin, hot enough to glow if it were dense enough to see. We've measured its motion. It's flowing past the sun at about 50,000 miles per hour. But we don't know its exact boundaries. We don't know how thick it is. We don't know how uniform it is. We don't know if the solar system is near the edge or deep in the center. And that matters. Because if the sun is about to exit the local interstellar cloud, the radiation environment around Earth will change. The density of neutral hydrogen will drop. The cosmic ray flux will shift. The pressure on the heliosphere will decrease and the heliopause might expand outward. Or if the sun is moving deeper into the cloud, the opposite might happen. Higher density, more pressure, a compressed heliosphere, increased radiation exposure. We don't know which scenario we're in, and Voyager is the only tool we have to find out. By measuring the density of the interstellar medium at increasing distances, by sampling the magnetic field orientation, by detecting changes in the plasma environment, Voyager is mapping the structure of the local interstellar cloud in real time. And in the next 10 years, as it travels another 3 billion miles deeper, it's going to tell us whether the cloud is thinning or thickening, whether we're approaching an edge or entering a denser core. That information has consequences beyond pure science, because the local interstellar cloud isn't the only structure out there. The galaxy is full of these clouds, dense regions and voids, hot bubbles and cold molecular clouds. The sun has been drifting through them for billions of years, and it will continue drifting through them for billions more. But some of those clouds are much denser than the local interstellar cloud. Some are cold molecular clouds, regions where the density spikes to thousands of atoms per cubic centimetre, where temperatures drop to 10 Kelvin, where stars are born and planets form. If the solar system ever drifts into one of those clouds, the heliosphere would collapse. The heliopause, currently 15 billion miles out, would compress inward to maybe 2 or 3 billion miles. The outer planets, Jupiter, Saturn, Uranus, Neptune, would be directly exposed to interstellar radiation. The cosmic ray flux at Earth would spike. The radiation dose on the surface would increase. The upper atmosphere would be bombarded by high-energy particles. We don't think that's happened in Earth's recent history, but we can't be sure, because we don't have a complete map of the solar system's path through the galaxy. We don't know every cloud it's passed through. We don't know the timeline of when the heliosphere has expanded and contracted over geological timescales. But Voyager is giving us the data to start building that map. By sampling the local environment, by measuring how the interstellar medium varies over distances of billions of miles, by detecting the gradients and transitions and boundaries, Voyager is teaching us how to read the structure of the galaxy. And in 10 years, when the power runs out, we'll have a snapshot, a single transect, A narrow slice of data showing what interstellar space looks like along one specific trajectory at one specific moment in cosmic history. It's not a complete map. It's not a comprehensive survey. It's a single line drawn through the galaxy. But it's the only line we have, the only direct measurement, the only ground truth. And every scientist working with Voyager data knows that this is it. This is the one chance. There are no follow-up missions planned. No Voyager 3 or Voyager 4 waiting in the wings. No next-generation interstellar probe scheduled for launch. NASA has proposed missions. The interstellar probe concept would use modern propulsion to reach 1,000 astronomical units in 50 years, 6 times faster than Voyager. It would carry advanced instruments. It would have higher power. It would be designed from the ground up for interstellar exploration. But it's not funded. It's not built. It's not even officially approved. It exists only in PowerPoint presentations and engineering studies. Which means Voyager, is it? For the foreseeable future, for the next several decades at least, Voyager is the only emissary we have in interstellar space, the only sensor, the only voice. And it's running out of time. But even as the power drains and the signal fades, Voyager is still making discoveries, still detecting phenomena we didn't predict, still forcing us to revise our models of how the galaxy works. One of the most recent discoveries is about electrons. Specifically, high-energy electrons accelerated to near-light speeds by processes we don't fully understand. Voyager's low-energy charged particle instrument has been detecting bursts of these electrons ever since it crossed the heliopause, not a steady stream. Bursts. Sudden spikes in counts that last for days or weeks, then fade back to background levels. At first, scientists thought these were just statistical noise, instrument glitches, cosmic ray contamination. But the pattern is too consistent, too structured. The bursts correlate with changes in the magnetic field. They appear and disappear in sync with the plasma wave oscillations. They're real. The working hypothesis is that these electrons are being accelerated by magnetic reconnection events, regions where the sun's magnetic field, still present even in interstellar space, stretched and tangled into long filaments, collides with the galaxy's magnetic field. When those fields reconnect, they release energy, lots of energy, enough to accelerate particles to enormous speeds. This is the same process that drives solar flares, the same physics that creates auroras on Earth. But it's happening out here in the interstellar medium, 15 billion miles from the Sun, where we never expected the Sun's magnetic field to still have any influence. And it's telling us something profound. The Sun's reach extends further than we thought. The heliosphere isn't just a bubble of solar wind. It's a magnetic structure, a network of field lines that stretch and twist and reconnect across distances we're only beginning to measure. And those magnetic structures matter because they influence how cosmic rays propagate, how energy flows through the galaxy, how the Sun interacts with its environment. But here's the unsettling part. We don't know how far those magnetic structures extend. We don't know if Voyager has already passed through the last of them or if they continue for billions more miles. We don't know if the Sun's magnetic field is still detectable at 20 billion miles, at 30 billion, at 50 billion. And we won't know, because Voyager will be dead long before it reaches those distances. The current trajectory puts Voyager 1 on a path toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light years of a star called AC plus 793888. That's closer than the Sun's nearest neighbour, Proxima Centauri. Close enough that if that star has planets, Voyager might, in some impossibly distant future, pass through their outer solar system. But by then Voyager will have been silent for tens of thousands of years, its instruments frozen, its power long dead, its transmitter cold. It will be a derelict, a fossil, a monument to a species that once looked outward and wondered what was beyond. And yet, even in death, Voyager will carry a message, the Golden Record, a 12-inch gold-plated phonograph disc containing sounds and images of Earth, music, greetings in 55 languages, the cry of a newborn baby, the roar of a rocket launch, Chuck Berry's Johnny B. Goode, Carl Sagan, who helped design the record, called it a message in a bottle, a time capsule, a statement that we were here, that we existed, that we looked up at the stars and sent something back, but the Golden Record was never really meant to be found. The odds of an alien civilization stumbling across Voyager in the vastness of interstellar space are so close to zero that they might as well be zero. The record is symbolic, a gesture, a hope. What's not symbolic is the data, the measurements, the scientific discoveries Voyager is transmitting right now in real time as it falls deeper into the void. Those discoveries will outlive the spacecraft. They'll outlive the scientists who built it. They'll outlive everyone alive today because the data is being archived, stored, preserved, published in journals and databases and textbooks that will be read by students who haven't been born yet. And in 10 years, when the last transmission is received, when the last watt of power drains from the RTGs, when the signal finally fades below the noise floor and Voyager goes silent, that archive will be complete. A complete record of the first human object to enter interstellar space. The first direct measurement of the galaxy beyond the Sun's influence. The first ground truth for models of cosmic ray propagation, magnetic reconnection, plasma waves, and the structure of the local interstellar medium. It's not enough. It will never be enough. Every answer Voyager gives us raises 10 new questions. Every discovery reveals gaps in our understanding. Every data packet makes the silence that will follow even more painful. But it's what we have. And in the time remaining, the narrow, shrinking window between now and 2036, we're going to extract every possible insight from those final transmissions. Because the countdown isn't just about Voyager. It's about us. About how much we can learn before the opportunity vanishes. About how well we can prepare for the discoveries that will come after, when the next generation of missions, if they're ever built, push even deeper into the galaxy. The next 10 years are Voyager's final act. The last chapter, the closing movement of a symphony that began in 1977 and will end in silence. But before that silence comes, there are still discoveries to be made, still questions to be answered, still thresholds to cross, and the most important one might be just ahead. Because if Voyager reaches the bow shock, if it exists, if it's within range, if the instruments are still alive when it arrives, then everything we think we know about the solar system's place in the galaxy might change. The bow shock is the frontier, the edge of the Sun's influence, the point where the solar wind's pressure finally equals the interstellar medium's resistance. Beyond that, the Sun is just another star, another point of light, another anonymous member of the galactic community, and Voyager If it crosses that threshold, we'll be the first human-made object to exist in a region of space where the sun's gravity is the only thing still connecting it to home. No solar wind, no magnetic field, no particle pressure. Just gravity. And even that will fade, slowly, over millions of years, until Voyager is no longer orbiting the sun, but drifting freely through the galaxy. But that future is unimaginably distant. Right now, in 2024, Voyager is still tethered, still within reach, still transmitting. And the clock is ticking. 10 years, maybe 12. That's the window, that's the countdown, that's how long we have to answer the questions that will define humanity's understanding of interstellar space for the next century. The signal is fading, the power is draining, the instruments are failing one by one. But Voyager is still out there, still moving, still detecting, still teaching us what it means to leave home and never come back. And in the next 10 years, it's going to tell us things nobody is ready to hear. Let's talk about what happens when Voyager's plasma wave instrument detects something it shouldn't be able to detect. In October 2020, Voyager 1's plasma wave sensor picked up a faint, continuous hum. Not a burst, not a spike. A steady tone, a drone in the data that hadn't been there before. It was sitting at a frequency around 3 kHz, right in the middle of the instrument's detection range. At first, the team thought it was interference, maybe a software glitch, maybe noise from the spacecraft's own electronics bleeding into the sensor. But the signal was too clean, too persistent. It lasted for months. And when they analyzed it carefully, they realized what they were hearing. The ambient sound of interstellar space itself. Not sound in the way we experience it on Earth. There's no air in space, no medium for pressure waves to propagate through. But plasma, ionized gas, the electrically charged particles that fill the space between stars, can carry oscillations. Waves of electron density that ripple through the interstellar medium like vibrations through a solid. Voyager's plasma wave instrument detects those oscillations by measuring tiny voltage fluctuations across its antenna, and what it was hearing in 2020 was the background hum of the galaxy, the idle frequency, the baseline vibration of interstellar plasma at a density of about 0.1 electrons per cubic centimeter. This was a discovery nobody predicted, because we thought interstellar space would be quieter. We thought the plasma density would be too low to generate detectable oscillations. We thought the background hum would be buried in noise. But it's there, constant, measurable. And it's telling us something critical. The interstellar medium is not inert. It's not a passive void. It's an active, dynamic medium that vibrates with energy from sources we're only beginning to understand. And here's the part that matters for the countdown. That hum is changing. As Voyager moves deeper into interstellar space, the frequency shifts slightly, a few hertz here and there, but consistently. The pitch is rising, which means the plasma density is increasing. Voyager is moving into a denser region of the interstellar medium. That shouldn't be surprising. We know the local interstellar cloud isn't uniform. We know there are density gradients, but the rate of increase is faster than the models predicted, which suggests either Voyager is approaching a boundary or the structure of the cloud is more complex than we thought. If Voyager is approaching a boundary, the edge of the local interstellar cloud, then in the next few years, that hum could suddenly shift, drop in frequency, change in character. We could watch in real time as Voyager transitions from one interstellar environment to another, and if that happens, we'll see exactly how the galaxy is structured on scales smaller than anything we can observe with telescopes. Because telescopes can't resolve individual clouds at these distances, they see the average, the integrated light, the big picture, but Voyager is a point sensor. It samples the universe at a specific location at a specific moment. It tells us what's actually there, not what the models say should be there. And what's actually there is often stranger than the models predict. Take the magnetic field, for instance. Before Voyager crossed the heliopause, the models predicted that the interstellar magnetic field would be oriented in a specific direction, roughly parallel to the plane of the galaxy, following the spiral arms aligned with the flow of the local interstellar cloud. Voyager's magnetometer measured the field, and it was pointing the wrong way. Not slightly off, not within error bars, wrong. The field was perpendicular to the predicted orientation, rotated by nearly 90 degrees, and it was stronger than expected, about 5 microgauss, compared to the predicted 2 to 3 microgauss. That discovery forced a complete revision of the models, because if the magnetic field in our local neighborhood is stronger and oriented differently than we thought, that changes everything about how cosmic rays propagate, how the heliosphere is shaped, how energy flows through the galaxy. But here's the deeper problem. We don't know if that field orientation is local or global. We don't know if Voyager just happened to cross the heliopause in a region where the field is twisted, or if the field everywhere in the local interstellar cloud is oriented this way. And we won't know until Voyager samples a much larger volume of space, until it travels far enough to detect changes in the field direction, until it crosses enough boundaries to build a map. But the countdown is running. And in 10 years, Voyager will have only traveled another 3.5 billion miles. That sounds like a lot. It is a lot. But in the scale of the galaxy, it's nothing. It's a rounding error. It's a single pixel in an image billions of pixels wide. And yet, that single pixel might be the most important one we ever capture, because it's ground truth. It's direct measurement. It's reality, not theory. Every model of the galaxy, every simulation of cosmic ray propagation, every prediction of how stars interact with the interstellar medium is built on assumptions. Assumptions about density, about temperature, about magnetic field strength and orientation, about how energy flows and particles move. Voyager is testing those assumptions. One data point at a time, one crossing at a time, and every time the data contradicts the models, we have to revise, rebuild, start over. That's the nature of exploration. You can't predict what you'll find. You can only measure what's there and deal with the consequences. And one of the consequences of Voyager's magnetic field measurements is that we now know the galaxy's magnetic field is more complex than we thought, more tangled, more dynamic, which means modeling cosmic ray trajectories, predicting where high-energy particles come from and how they reach Earth, is harder than we assumed. Which brings us back to radiation. Back to the question of whether interstellar space is survivable. Right now, Voyager's cosmic ray detector is measuring particle fluxes at levels we've never sampled before, protons with energies in the giga-electron-volt range, helium nuclei, heavy ions, all of them slamming into the spacecraft at near-light speeds, depositing energy, degrading materials, creating secondary particles through collisions. The data shows that the cosmic ray flux outside the heliosphere is about 30% higher than the flux inside. That's not catastrophic. It's not unsurvivable, but it's significant and it's cumulative. A human traveling through interstellar space would be exposed to that radiation constantly. Every second, every minute, every hour, there would be no escape, no shelter, no planetary magnetosphere to hide behind. The question is, how much exposure can a human survive? The answer depends on shielding, on mission duration, on the specific energy spectrum of the particles, on biological factors like age and genetic susceptibility. But Voyager is giving us the data to start calculating those answers, because the cosmic ray detector isn't just counting particles, it's measuring their energy, their composition, their arrival directions. It's building a complete profile of the interstellar radiation environment, and in the next 10 years, as Voyager moves deeper, it's going to refine that profile. It's going to tell us whether the radiation environment is stable or variable, whether there are hot spots and cold spots in the galaxy, whether the density of cosmic rays increases smoothly with distance from the Sun, or whether there are sudden jumps at specific boundaries. That information is critical for mission planning. Because if we ever want to send humans to another star, not just robots, but living people, we need to know what they'll face. We need accurate radiation maps. We need to know the dosages, the exposure timelines, the risk profiles. And right now, Voyager is the only source of that data, the only spacecraft that's actually out there measuring the environment humans would have to survive in. But Voyager wasn't designed for this. It wasn't built to be a radiation safety probe. It was built to study Jupiter and Saturn. Everything it's doing now, every measurement of interstellar space, is a bonus, an afterthought, a lucky accident made possible by the fact that the spacecraft refused to die. And that's the irony of Voyager's final decade. The most important discoveries, the most critical data, the measurements that will shape humanity's future in space are all coming from a machine that was never meant to survive this long. The engineers who built Voyager in the 1970s designed it to last 5 years, maybe 10. They didn't reinforce it for interstellar radiation. They didn't add redundant systems for long-term operation. They didn't plan for a scenario where the spacecraft would still be transmitting data half a century later. And yet here it is, still working, still alive, still teaching us things we never thought to ask. That's not just luck. That's over-engineering. That's the product of a mindset that said, build it better than it needs to be, because you never know. That's the legacy of an era when NASA had the budget and the mandate to build things that would last. And now, as Voyager enters its final decade, as the power drains and the instruments fail one by one, we're seeing the limits of that engineering. We're seeing what happens when you push 1970s technology to its absolute breaking point. The cosmic ray detector is operating 45 degrees Celsius below its design limit. The magnetometer is running on backup power. The plasma wave instrument is held together by software patches and prayer. The transmitter is broadcasting at a frequency it was never meant to sustain for this long. Every day that Voyager continues to operate is a small miracle. Every data packet that reaches Earth is a victory against entropy. And the scientists who monitor Voyager's health, the engineers who manage its power budget, who schedule its transmissions, who troubleshoot its glitches, know that every decision they make could be the one that determines whether Voyager lasts another month or another year. In 2022, Voyager 1 started sending back corrupted data. The telemetry was garbled, nonsensical. The spacecraft's attitude control system, the system that keeps the antenna pointed at Earth, was reporting impossible orientations. The numbers didn't make sense. For months, the team struggled to diagnose the problem. They sent commands. They ran tests. They analyzed the signal. Nothing worked. And then they found it. A single corrupted byte in the spacecraft's memory. One bit flipped from a 0 to a 1, probably by a cosmic ray impact. That single bit error had cascaded through the system, creating gibberish in the telemetry stream. They fixed it by uploading a software patch, a new set of instructions telling the spacecraft to ignore the corrupted memory location and use a backup instead. The telemetry cleared. The data started making sense again. Crisis averted. Disaster postponed. But that incident was a warning, a reminder that Voyager is fragile, that a single cosmic ray hitting the wrong transistor at the wrong moment could cripple the entire mission. And cosmic rays are everywhere in interstellar space. Voyager is flying through them constantly. Every second, dozens of high-energy particles are slamming into the spacecraft, penetrating its aluminum skin, colliding with its electronics, flipping bits in its memory. Most of those impacts are harmless. The spacecraft has error-correcting codes, redundant systems, shielding. But eventually, inevitably, one of those impacts will hit something critical, a processor, a memory chip, the transmitter itself. And when that happens, there's no repair mission, no way to fix it. Voyager is 15 billion miles away. The light time delay is over 22 hours. By the time we know something is broken, it's already been broken for a full day. All we can do is watch and hope and make the most of the time we have left. Which brings us to one of the most urgent questions in Voyager's final countdown. What should we prioritize? The spacecraft has limited power, limited bandwidth, limited time. Every decision to run one instrument means shutting down another. Every choice to transmit one dataset means delaying another. So, what should we focus on? The cosmic ray detector measuring radiation levels for future missions? The magnetometer mapping the interstellar magnetic field? The plasma wave instrument listening for the hum of the galaxy? There's no right answer. Every instrument is providing irreplaceable data. Every measurement is unique. Every data point could be the one that unlocks a critical insight. But the team has to make choices, and they're making them based on science priorities, power budgets, and gut instinct. Right now, the cosmic ray detector and the magnetometer are considered the highest priority. They're providing the most novel data. The measurements that are hardest to replicate with other instruments or methods. The plasma wave instrument is still running, but it's on a reduced duty cycle. It only activates for a few hours per week, sampling the interstellar hum in short bursts rather than continuously. The ultraviolet spectrometer was shut down in 2016. It was designed to study planetary atmospheres, Jupiter, Saturn, their moons. Once Voyager left the planets behind, it became redundant, dead weight, a drain on power that could be better used elsewhere. The infrared radiometer was shut down even earlier, in 2007. Same reason, no planets to study, no targets in range. One by one, the instruments are being sacrificed, turned off to extend the mission to keep the critical sensors alive a little longer, and each shutdown is a small death, a piece of Voyager's capability lost forever, a narrowing of the mission's scope. But it's necessary. Because if they kept everything running, the power would run out faster. The mission would end sooner, and we'd lose years of data from the instruments that matter most. It's triage, resource management, the cold calculus of exploration. And in 10 years, when the last instrument shuts down, when the transmitter finally goes dark, the scientists who've spent their careers working on Voyager will have to face a reality they've been dreading for decades. Their life's work is ending. For some of them, Voyager has been their entire professional identity. They were graduate students when the spacecraft launched. They built their careers analyzing its data. They've spent 47 years watching it fly deeper into the void, waiting for the next discovery, the next surprise, the next breakthrough. And now they're watching it die. Slowly, inevitably, 1 watt at a time. There's grief in that, real grief. The kind you feel when something you love is slipping away and there's nothing you can do to stop it. But there's also gratitude, because Voyager gave them something most scientists never get: a complete mission, a beginning, a middle, and an end. A story arc that spans a human lifetime. Most space missions fail. Most spacecraft break. Most experiments don't work. But Voyager worked. For 47 years and counting, it worked so well that it exceeded every expectation, every goal, every dream. And in its final decade, it's still working. Still surprising us, still teaching us, still reminding us why we explore in the first place. Because the universe is stranger than we imagine. Because the galaxy is more complex than our models predict. Because every time we send something beyond the edge of human experience, it comes back with news that changes everything. And Voyager's news, the discoveries it's making right now, the data it's transmitting in its final years, is going to echo for generations. Because this is the baseline, the ground truth. The first direct measurement of interstellar space. Every future mission will be compared to Voyager. Every model will be tested against Voyager's data. Every prediction will be judged by whether it matches what Voyager found. And when the next interstellar probe finally launches, if it ever launches, it will be following in Voyager's footsteps. Literally. It will fly along a similar trajectory, sample similar regions, look for the same boundaries and transitions, but it will have the advantage of Voyager's legacy. It will know where to look, what to expect, what questions to ask, and that legacy is being written right now in the data packets arriving at the Deep Space Network, in the measurements of cosmic rays and magnetic fields and plasma waves, in the slow, patient accumulation of knowledge about a region of space no human-made object had ever touched before Voyager arrived. 10 years left. Maybe 12. That's the countdown. That's the window. That's how long we have to complete the archive. And then silence. Voyager will keep moving, keep traveling, keep falling through the galaxy at 38,000 miles per hour, but it will be alone, unheard. A ghost ship drifting through the void with no way to tell us what it sees. And we'll be left with the data, the archive, the memory of a time when humanity reached beyond itself and touched something vast and ancient and utterly indifferent to our existence. That's Voyager's legacy, not the golden record, not the pretty pictures of Jupiter and Saturn, the data, the science, the knowledge that will outlive all of us. And in the final years of the countdown, as the power drains and the signal fades, that legacy is still being written, one data point at a time, one discovery at a time, one transmission at a time, until there are no more transmissions, until the silence becomes permanent, until Voyager is just another piece of space debris, indistinguishable from the countless asteroids and comets and fragments of rock that drift through the galaxy, forgotten and alone. But not yet. Not for 10 more years, not while there's still power in the RTGs and data, in the recorders and scientists on Earth listening for the faintest whisper from the edge of forever. The countdown continues, and Voyager is still out there, still detecting, still teaching us what nobody is ready to hear. There's a question that haunts every scientist working with Voyager data, and it's not the one you'd expect. It's not, what will we discover? It's not, how much time do we have left? It's this. What if Voyager is detecting something right now that we won't understand until it's too late to ask follow-up questions? This is the nightmare scenario of single-point exploration. Voyager is alone out there. It's the only sensor, the only witness. If it detects something anomalous, something that doesn't fit the models, something that raises more questions than answers, we can't send another probe to verify. We can't adjust the instruments. We can't change course to investigate further. We can only watch and wonder and hope the data makes sense before the mission ends. This isn't hypothetical. It's already happened. In 2012, when Voyager 1 crossed the heliopause, the plasma wave instrument detected a sudden jump in electron density. The numbers spiked. The models said this was it, the boundary, the transition from solar-influenced space to true interstellar space. But the magnetometer told a different story. The magnetic field didn't rotate, didn't change direction. The models predicted the field would flip from the sun's magnetic orientation to the galaxy's, but it didn't. It stayed pointed in the same direction. For months, scientists argued about what this meant. Had Voyager actually crossed the heliopause, or was this just a temporary fluctuation? Was the magnetic field data wrong, or were the models wrong? Eventually, they concluded that the models were incomplete, that the heliopause crossing doesn't require a magnetic field rotation, that the transition is more complex than a simple boundary flip. But here's the problem. We only have one data point, one crossing. Voyager 1's experience. And then, 6 years later, Voyager 2's crossing, which was different. The magnetic field behaved differently. The plasma densities were different. The timing relative to the solar cycle was different. 2 crossings, 2 different experiences. And from that, we're supposed to build a universal model of how heliospheres work. It's not enough. It will never be enough. But it's all we have, and in Voyager's final decade, this problem is only getting worse, because the deeper Voyager goes, the more unique its measurements become. The less context we have, the fewer reference points. If Voyager detects the bow shock, we'll have one observation, one crossing, one data set, and from that single event we'll be expected to extrapolate to every other star in the galaxy, to predict how bow shocks form, how they evolve, how they interact with the interstellar medium. That's an impossible task, but it's the task we've signed up for, because Voyager is all we've got. And this raises a deeper philosophical question about exploration itself. Is a single data point better than no data point at all? Most scientists would say yes. Obviously, yes. One measurement is infinitely more valuable than 0 measurements. One ground truth is worth 1,000 models. But there's a counter-argument. A single data point can be misleading. It can create false confidence. It can make you think you understand something, when all you've really done is measure one specific instance of a phenomenon that might vary wildly under different conditions. Voyager's measurements of the heliopause are a perfect example. We measured it. We know what it looked like at 2 specific locations at 2 specific times during 2 specific phases of the solar cycle. But what does the heliopause look like on the opposite side of the solar system? What does it look like during solar maximum, when the sun's output is at its peak? What does it look like 1 billion years ago? when the sun was younger and hotter? What does it look like for other stars? Red dwarfs, blue giants, binary systems? We don't know. We can't know, because we only have two data points, two measurements, two narrow slices of a phenomenon that extends across billions of miles and billions of years. And yet, those two data points have already revolutionized our understanding of how stars interact with the galaxy. They've forced us to revise our models, to question our assumptions, to admit that we were wrong about fundamental aspects of heliospheric physics. That's the power of exploration. Even incomplete data, even a single measurement, can shatter paradigms. But it also creates pressure, enormous pressure, because every scientist working with Voyager data knows that this is their one chance, their only chance. There will never be another opportunity to measure these phenomena with the same level of detail, at the same locations, under the same conditions. So they have to get it right. They have to extract every possible insight from the data. They have to publish papers and build models and train the next generation of researchers before the mission ends and the data stream stops. And they're racing against time. Because Voyager isn't just running out of power, it's running out of relevance. That sounds harsh, but it's true. Science moves fast. New missions launch, new instruments come online, new techniques are developed, and every year Voyager's data becomes a little more historical, a little less cutting edge. The cosmic ray measurements from 2024 are valuable. But the cosmic ray measurements from 2034, when Voyager is 3 billion miles deeper into interstellar space, will be even more valuable. And if the mission ends before we reach those depths, we'll never know what we missed. This is the cruel mathematics of exploration. The most important discoveries are always just ahead, just out of reach, just beyond the mission's lifespan. But there's another layer to this countdown that most people don't think about: the human infrastructure that supports Voyager. The Deep Space Network isn't just 3 antennas sitting in the desert. It's a massive, complex system involving hundreds of people. Engineers who maintain the dishes, technicians who calibrate the receivers, software developers who write the decoding algorithms, scientists who analyze the data, and all of those people are aging, retiring, moving on to other projects. The engineers who built Voyager are in their 70s and 80s now. Many have already passed away. The scientists who designed the experiments are emeritus professors, if they're still alive at all. The institutional knowledge, the deep, intuitive understanding of how the spacecraft works, what its quirks are, how to interpret anomalies, is disappearing. NASA has been trying to preserve that knowledge. They've recorded interviews with the original engineers. They've digitized old documents. They've created training programs for younger staff. But there's no substitute for experience, for having lived with the spacecraft for decades, for having troubleshot its problems in real time, late at night under pressure, when every decision could mean the difference between mission success and mission failure. When Voyager finally goes silent, that institutional knowledge will become frozen, fixed, a historical artifact rather than a living tradition, and future missions, if they're ever flown, will have to start from scratch. They'll have Voyager's data, Voyager's papers, Voyager's archive, but they won't have Voyager's people. That's a loss that's hard to quantify, but it's real, and it's part of the countdown. 10 years left, maybe 12. And in that time, not just the spacecraft, but the entire human system around the spacecraft is approaching its end state. But let's shift focus. Let's talk about what Voyager might detect in its final years that could change everything we think we know about the galaxy. One possibility: a density transition. Right now, Voyager is moving through the local interstellar cloud at a density of about 0.1 electrons per cubic centimetre. That's already higher than the average interstellar medium, which clocks in at about 0.01 electrons per cubic centimetre. But the local interstellar cloud isn't the only structure in this region. We're inside the local bubble, that 300 light-year cavity carved by ancient supernovae. And the local bubble has boundaries, walls, regions where the density spikes to much higher levels. If Voyager reaches one of those boundaries, the plasma density could suddenly increase by a factor of 10 or 100. The hum that Voyager's plasma wave instrument detects could shift dramatically. The cosmic ray flux could drop because denser plasma is more effective at scattering high-energy particles. The magnetic field could reorient because dense regions have different field configurations. That transition, if it happens, then would be the interstellar equivalent of crossing the heliopause, a boundary between environments, a threshold between regimes. And it could happen within the next 10 years, because we don't know exactly where the boundaries are. We don't know how far Voyager has to travel to reach them. If Voyager crosses that boundary while its instruments are still alive, we'll witness the transition in real time. We'll see the data shift. We'll watch the plasma hum change frequency. We'll measure the exact structure of the boundary layer, and from that single observation, we'll learn more about the architecture of the local bubble than we've learned from decades of telescope observations. But if Voyager doesn't reach the boundary before the power runs out, we'll be left wondering. How far is it? What does it look like? What happens on the other side? Another possibility, a magnetic field reversal. The interstellar magnetic field that Voyager has been measuring for the past 12 years is strong and relatively stable. It's pointed in a direction that doesn't match the models, but it's consistent, steady. But magnetic fields aren't static, they're dynamic. They twist and reconnect and evolve over time and space. And there's no reason to assume the field orientation Voyager is measuring right now is the same orientation it will measure 5 years from now, or 10. If the field reverses, if Voyager enters a region where the magnetic polarity flips, the effects would be immediate and dramatic. Cosmic ray trajectories would change, particle fluxes would spike or drop, the plasma wave oscillations would shift, and we'd have no way to predict when or where this reversal might happen. No way to prepare. We'd just watch the data change and scramble to understand what it means. This is the reality of exploring the unknown. You can't anticipate every discovery. You can't plan for every contingency. You can only respond, adapt, learn, and hope you have enough time to figure it out before the mission ends. Another possibility, and this is the one that keeps astrobiologists awake at night, is that Voyager might detect organic molecules. The interstellar medium isn't empty. It's not just hydrogen and helium. There are complex molecules out there. Carbon chains, aromatic hydrocarbons, amino acid precursors. The building blocks of life drifting through the void, synthesized in the atmospheres of dying stars and scattered across the galaxy by supernova explosions. We've detected these molecules with radio telescopes. We know they're out there, but we've never sampled them directly. We've never measured their density, their distribution, their isotopic composition at a specific location in interstellar space. Voyager's instruments weren't designed to detect organic molecules. The mass spectrometer that could have done the job was removed during the design phase to save weight, but the plasma wave instrument can detect ionized molecules, and the cosmic ray detector can identify heavy ions, which might include fragments of complex organics. If Voyager happens to pass through a region with a high concentration of organic molecules, the instruments might pick up a signal. Indirect, ambiguous, but a signal nonetheless. And if that happens, it will raise the most profound question in all of science. How common is the chemistry of life in the galaxy? Because if organic molecules are abundant in the interstellar medium, if they're everywhere, drifting through the void, waiting to be swept up by forming star systems, then the emergence of life might not be a rare accident, it might be inevitable, baked into the fabric of the universe. But we won't know until we measure it, until we sample the interstellar medium directly and catalogue what's actually there. And Voyager, in its final years, might give us the first hint of an answer. Or it might not. It might drift through a region that's chemically barren, or it might detect something but lack the instruments to identify it properly. Or it might run out of power before it reaches a region where organic molecules are concentrated. This is the frustration of exploration. You never get to choose what you find. You can only go where the trajectory takes you and measure what's there when you arrive. And Voyager's trajectory was set 47 years ago. Locked in by gravity assists at Jupiter and Saturn, there's no steering, no course corrections. No way to say, turn left, at the interesting nebula. Voyager is ballistic, a thrown rock, an arrow shot into the dark, and wherever it lands, that's what we get to measure. But here's the thing. Even if Voyager doesn't detect anything new in its final years, even if the data in 2034 looks exactly like the data in 2024, that's still valuable. Because stability is information. Uniformity is information. Knowing that the interstellar medium doesn't change dramatically over distances of billions of miles tells us something fundamental about the structure of the galaxy. It tells us the local interstellar cloud is more homogeneous than we thought. It tells us the magnetic field is more stable. It tells us the plasma density doesn't fluctuate wildly. And that information constrains the models. It narrows the possibilities. It helps us understand what kinds of processes can and can't happen in interstellar space. So even a null result, even a decade of data that shows nothing changing, is a result. It's an answer to a question we didn't know we were asking. But let's be honest, nobody wants a null result. The scientists working on Voyager don't want to spend the mission's final years watching flat, unchanging data streams. They want discoveries, surprises, anomalies that force them to rethink everything. Because that's what science is about, not confirming what you already believe, not validating the models, but finding the places where the models break, where reality refuses to cooperate, where the universe says, "You thought you understood me, but you were wrong." And Voyager has been saying that since the beginning. Since the first images of Jupiter's moons revealed active volcanism on Io. Since the first close-ups of Saturn's rings showed structure nobody predicted. Since the first measurements beyond the heliopause revealed a magnetic field pointing the wrong way. Voyager's legacy is a legacy of surprises. And in its final decade, there's no reason to expect that to change. But there's also no guarantee. The universe doesn't owe us discoveries. It doesn't care about our curiosity or our budgets or our timelines. The universe just is. And Voyager is just a machine, drifting through it, measuring what it measures, transmitting what it transmits, until the power runs out and the signal stops. And when that moment comes, when the last data packet is received, when the telemetry flatlines, when the deep space network antennas listen for Voyager's signal and hear nothing, it will mark the end of an era, the era of the first interstellar emissary, the first human-made object to leave the solar system and sample the galaxy beyond. There will be others, eventually. The technology will improve, the budgets will materialize, the missions will launch, but Voyager will always be the first, the pioneer, the trailblazer, and in 10 years, that trail will end. The transmissions will stop, the data will go silent, but the discoveries will continue, because the data we've already received, the archive we've already built, will be analyzed for decades. Generations of scientists will pore over Voyager's measurements, finding patterns we missed, asking questions we didn't think to ask, extracting insights that won't become obvious until we have more context from future missions. Voyager's data is a time capsule, not just for the golden record, but for the science. It's a snapshot of the interstellar medium in the early 21st century, measured with the best instruments humanity could build in the 1970s, transmitted across billions of miles, archived for posterity. And that archive is still growing. Every day, new data arrives. New measurements are added to the record. The snapshot becomes more complete, but only for 10 more years. After that, the snapshot is final, frozen, complete. And whatever we missed, whatever Voyager didn't have time to measure, will remain unknown until the next mission. If there is a next mission, and that's the most haunting part of the countdown, because there's no guarantee, no promise that humanity will continue exploring interstellar space, no certainty that we'll build the next probe, launch the next mission, send the next emissary into the void. We might not. We might decide it's too expensive, too difficult, too far beyond our current capabilities. We might turn inward, focus on Earth, on the Moon, on Mars, on the problems and crises and challenges that feel more immediate, more urgent, more relevant to daily life. And if that happens, Voyager's silence won't just mark the end of a mission, it will mark the end of humanity's presence in interstellar space. For decades, maybe centuries. That's the weight of the countdown. That's what's at stake. Not just the data, not just the discoveries, but the continuation of a dream. The dream that we can reach beyond ourselves, that we can touch the stars, that we can understand our place in the cosmos. Voyager kept that dream alive for 47 years, and in its final 10 years, it's still keeping it alive, still inspiring, still reminding us why we explore, because the universe is vast and strange and beautiful and terrifying. And the only way to understand it is to go there, to measure it, to sample it, to send our machines into the void and listen to what they tell us. And Voyager is still telling us, still transmitting, still teaching. But the clock is ticking, and the silence is coming. Let's talk about what happens after the silence, because the countdown to Voyager's final transmission isn't just an ending, it's also a beginning. The beginning of Voyager's longest journey, the one that will last billions of years, long after humanity itself might be gone. When the power finally drains from the RTGs, when the last instrument shuts down, when the transmitter goes dark and Voyager can no longer tell us what it sees, the spacecraft will continue moving. It won't stop. It can't stop. There's no friction in space, no air resistance, no force to slow it down. Voyager 1 will keep travelling at 38,000 miles per hour. Voyager 2 at 34,000 miles per hour. Forever, or at least until they collide with something, which in the vast emptiness of interstellar space could take trillions of years. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. It won't be close enough to be captured by the star's gravity. It will just drift past, silent and dark, a dead machine in the night. In 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in Earth's sky. Again, too far for gravitational capture. Just a flyby, another anonymous piece of debris in the galaxy's endless night, and then, for millions of years, nothing, just the slow drift through the void, passing between stars, crossing the spiral arms of the Milky Way, rising and falling through the galactic plane like a cork bobbing in an ocean. Eventually, maybe in a few billion years, Voyager will encounter a molecular cloud, a dense region of gas and dust, and when it does, the spacecraft will be sandblasted, stripped, eroded by collisions with dust grains moving at relative speeds of tens of thousands of miles per hour. The golden record will be pitted, scratched, maybe destroyed entirely. The spacecraft's aluminum skin will be worn away, the instruments will be reduced to fragments, the entire structure will slowly disintegrate, atom by atom, scattered across light years. But even then, some pieces might survive. Tungsten components, plutonium pellets from the RTGs which will still be radioactive for millions of years, fragments of the record itself, now just shards of gold-plated copper drifting alone. And in some unimaginable future, billions of years from now, one of those fragments might encounter something. Another star system, a forming planet, a comet's tail, and it will be captured, swept up, incorporated into whatever structure is assembling itself from the raw materials of the galaxy. Voyager's atoms will become part of a planet, or a moon, or a comet, or the atmosphere of a star, and in that sense, Voyager will never truly die. It will just transform, return to the cosmic cycle, become part of the galaxy it spent its operational life measuring. That's the deep future, the timeline measured in billions of years, the countdown that started the moment Voyager launched and won't end until the universe itself ends. But before we get lost in that cosmic timescale, let's come back to the next 10 years. Because those 10 years, the human relevant countdown, the window we actually get to witness, are going to determine how we remember Voyager, how we honor it, how we use its legacy. And one of the most important questions facing the Voyager team right now is this: how do we maximize the science return in the time remaining? Because the power budget forces choices, hard choices. Every watt spent on one instrument is a watt not available for another. Every day of operations for one sensor is a day lost for a different one. Right now, the priority is the cosmic ray detector and the magnetometer. Those are providing the most unique data, the measurements that can't be replicated any other way. But what about the plasma wave instrument? It's been running on a reduced schedule, sampling only intermittently. Should they increase its duty cycle, sacrifice some cosmic ray measurements to get more plasma data? What about the engineering telemetry, the temperature sensors, the voltage monitors, the systems that track the spacecraft's health? Should they shut those down entirely to free up power for science? Or do they keep them running to monitor Voyager's degradation, to learn how spacecraft age in interstellar radiation? These aren't easy questions, and the team debates them constantly. Every year, they reassess. Every year, the calculus changes as the power drops, and the mission priorities evolve. But there's another consideration that's equally important: data processing and archiving. Because receiving the data is only half the battle. You also have to decode it, calibrate it, correct for instrument drift and radiation damage and temperature variations, You have to convert raw voltages into physical measurements. You have to account for the spacecraft's changing orientation, its distance from the Sun, the properties of the interstellar medium it's sampling, and all of that takes time, and people, and funding. Right now, there are researchers who've spent years developing algorithms to extract weak signals from Voyager's noisy data streams, to identify plasma waves in the static, to measure cosmic ray energies from degraded detector outputs, to reconstruct magnetic field orientations from instruments that were never designed to operate at these temperatures. Those researchers are doing heroic work. They're squeezing every possible bit of information from data that's barely above the noise floor. They're finding patterns that would be invisible without sophisticated analysis techniques, but they're not immortal. And their funding isn't infinite. When Voyager goes silent, the data stream stops, but the analysis continues for years, maybe decades. Because there's always more to extract, always deeper patterns to find, always new questions to ask of old data. But eventually, the funding dries up. The researchers move on to other projects, the institutional knowledge fades, and the data becomes historical, archived, preserved but no longer actively studied. That transition from living science to historical archive is inevitable. It happens to every mission, but it doesn't have to happen immediately. If we're smart, if we plan ahead, we can keep Voyager's data alive for generations. We can create fellowships for young scientists to analyze the archive. We can build machine learning tools to find patterns humans might miss. We can integrate Voyager's measurements into broader models of the galaxy, using them as ground truth for simulations and predictions. We can make sure that Voyager's legacy isn't just the spacecraft that went to interstellar space and sent back data. We can make it the mission that fundamentally changed how we understand our place in the galaxy. But that requires commitment, resources, vision, and right now, in 2024, with 10 years left on the countdown, we're at a critical juncture. Because the decisions we make now about funding, about data archiving, about training the next generation of researchers will determine whether Voyager's legacy endures or fades. So let's talk about what we've learned. Let's take stock of Voyager's discoveries in interstellar space and understand what they mean for humanity's future. First, the heliosphere is smaller and more dynamic than we thought. The boundary between the Sun's influence and the galaxy's domain isn't a fixed shell. It's a breathing membrane that expands and contracts with the solar cycle. It pulses, it fluctuates, and that means Earth's radiation environment is more variable than we assumed. Second, the interstellar magnetic field is stronger and oriented differently than the models predicted. That changes everything about cosmic ray propagation. It means high-energy particles don't travel in straight lines through the galaxy. They spiral, they scatter. They're guided and deflected by magnetic structures we're only beginning to map. Third, interstellar space isn't empty. It's filled with plasma, with waves, with structure. There's a hum to the galaxy, a background oscillation that's constant and measurable. And that hum tells us about the energy flowing through the interstellar medium, about shock waves from distant supernovae, about processes happening on scales we can barely comprehend. Fourth, the radiation environment outside the heliosphere is harsher than we hoped. Cosmic ray fluxes are 30% higher than inside the solar bubble, and they're increasing as Voyager goes deeper, which means long-duration space travel beyond Earth's magnetosphere is going to be more dangerous than we'd like to admit. Fifth, we were wrong about a lot of things. The bow shock might not exist where we thought it did. The heliopause crossing doesn't look like the models predicted. The magnetic field doesn't rotate at the boundary. Every assumption we made based on theoretical models has had to be revised, questioned, or thrown out entirely. And that's the most important lesson of all. Direct measurement beats theory every single time. You can build the most sophisticated model in the world. You can run simulations on supercomputers. You can have equations that predict every detail of how the heliosphere should behave. But if you don't send a spacecraft out there to actually measure it, you're just guessing. Educated guessing, sophisticated guessing, but guessing nonetheless. Voyager stopped the guessing. It gave us ground truth. And in doing so, it revealed how much we didn't know. And in its final 10 years, it's going to reveal even more gaps in our knowledge, even more places where reality refuses to match the models, even more reasons to question our assumptions. Because that's what exploration does. It doesn't just answer questions, it reveals how poorly we understood the questions in the first place. And the questions Voyager is forcing us to confront are fundamental. What is the structure of interstellar space? How does the sun interact with the galaxy? How do cosmic rays propagate? What are the boundaries of the solar system? Where does the sun's influence end and the galaxies begin? We thought we knew the answers to these questions. We had models, theories, predictions. But Voyager showed us we were wrong, or at least incomplete, or at least overconfident. And that humility, that recognition that the universe is more complex than we imagined, is Voyager's greatest gift, because it keeps us humble. It keeps us curious. It keeps us asking questions instead of assuming we already know the answers. And in 10 years, when Voyager goes silent, that gift will become permanent, frozen in time. A snapshot of what one moment of human curiosity achieved when we were brave enough to send something beyond ourselves and listen to what it told us. But here's the question that lingers. What comes next? When Voyager's transmission ends, when the deep space network antennas finally hear nothing but noise, what do we do? Do we build the next probe? Do we launch the interstellar mission, the faster, more advanced successor that could reach 1,000 astronomical units in a human lifetime? Do we invest in bigger antennas so we can keep listening for fainter signals, extending the contact time with future missions? Do we turn inward, focus on Mars and the Moon and near-Earth space, and accept that interstellar exploration is a luxury we can't afford? Right now, the answer is unclear. NASA's budget is stretched, priorities shift, administrations change. The political will to fund long-term, high-risk science missions waxes and wanes. But Voyager makes the case. Every discovery it transmits, every boundary it crosses, every anomaly it detects, all of it argues for continuing the journey, for sending the next mission, for not letting the silence become permanent. Because if we stop now, if Voyager's silence marks the end of humanity's presence in interstellar space, we'll be abandoning the frontier just as it was starting to reveal its secrets. We'll be like explorers who reached the shore of a new continent, took a few measurements, and then sailed home without ever venturing inland. We'll have proven it could be done, but we won't have followed through, and future generations will look back and wonder, why did they stop? Why did they let Voyager be the last? Why didn't they build on what they'd learned and go further? We don't have good answers to those questions yet, because we're still in the middle of the story. We're still watching Voyager's countdown. We're still receiving the data, analyzing the discoveries, trying to understand what it all means. But in 10 years, we will have answers. We'll have to. Because the silence will force a decision. Either we commit to continuing the exploration, or we accept that Voyager was a singular achievement, never to be repeated. And that choice will say something profound about who we are as a species, about what we value, about whether we're the kind of civilization that keeps reaching outward or one that turns inward and stops. Voyager can't make that choice for us. It's just a machine, a tool, a messenger carrying our curiosity into the void. But the message it's sending back, the data, the discoveries, the revelations, is clear. The universe is vast and strange and full of wonders we've barely begun to understand. And the only way to understand it is to go there, to measure it, to explore it. That's Voyager's message. That's its legacy. That's what it's been telling us for 47 years, and what it will keep telling us for 10 more. And when the final transmission is received, when the signal fades into static and the silence settles in, that message won't disappear. It will echo through the data archives, through the scientific papers, through the textbooks and documentaries and museum exhibits, through the dreams of children who look up at the night sky and wonder what's out there, through the calculations of engineers designing the next generation of spacecraft, through the proposals of scientists arguing for the next mission, the next discovery, the next leap into the unknown. Voyager's silence won't be the end. It will be a pause, a moment to reflect, to honor what was achieved, to mourn what was lost, and then, if we're wise, if we're brave, if we remember why we sent Voyager in the first place, we'll continue. We'll build the next probe, launch it into the void, point it toward the boundary and tell it to go further than Voyager ever could. And we'll wait for years, for decades, for the signal to return, for the data to arrive, for the discoveries that will make us question everything we thought we knew. Because that's what exploration is. It's not about confirming what you already believe. It's about being surprised, being humbled, being forced to admit that the universe is stranger and more complex than you imagined. And Voyager has been surprising us for 47 years, humbling us, forcing us to revise and rethink and start over. In its final 10 years, it's going to keep doing that. Keep pushing boundaries, keep detecting the unexpected. And when it finally goes silent, when the power drains away and the transmitter stops and the instruments freeze in the absolute cold of interstellar space, it won't be a failure. It will be a triumph, a mission that exceeded every expectation, that outlived its designers, that became something nobody could have predicted when it launched in 1977. A 1970s spacecraft with 1970s technology, still operating in 2024, still transmitting across 15 billion miles, still teaching us about the galaxy we live in. That's not just engineering, that's not just science, that's human aspiration made manifest. It's proof that when we set our minds to something difficult and important, we can achieve the impossible. And in 10 years, when Voyager's journey through our awareness ends and it continues alone through the galaxy, that proof will remain. In the data, in the discoveries, in the legacy of the first human artifact to touch interstellar space and tell us what it found there. The countdown is running, the clock is ticking, the power is draining, but Voyager is still out there, still moving, still measuring, still transmitting. And for the next 10 years, we get to listen, we get to learn. We get to witness the slow, inevitable fade of humanity's most distant emissary as it falls deeper into the void and discovers things nobody is ready to hear. This is the final decade, the closing chapter, the last transmission. And when it comes, when the deep space network antennas strain to hear Voyager's whisper and find only silence, we'll know that an era has ended. The era of Voyager, the era of the first interstellar probe, the era when humanity reached beyond the solar system and touched the galaxy beyond. And we'll have to decide, was this the beginning of something greater, or was it the end? The answer is up to us. But Voyager has shown us the way. It's given us the map, the data, the discoveries. All we have to do is follow. And in the final 10 years of the countdown, as the signal fades and the silence approaches, Voyager is still pointing the way forward, still measuring the unknown, still teaching us what it means to explore, still reminding us why we look up at the stars and wonder what's beyond. The clock is ticking, the power is running out, the signal is fading, but the journey continues. For Voyager, for us, for the future generations who will inherit the knowledge we're gathering now and use it to go further than we ever dreamed possible. 10 years left, maybe 12, and then silence. But until then, Voyager speaks, and we listen, and we learn, and we prepare for what comes next.